So let me start by sharing the screen. Sorry, there's a little technical glitch. Good. Now it works. Can you see the screen?
Yes, we can.
Okay. I will stop the video just to save some bandwidth on my side, and then I continue with the screen sharing only. Okay. Good. So welcome to this first lecture on polylogs, elliptic polylogs, etc. As part of the amplitudes games this year held in Mainz. So maybe just to set the scene, let me start by introducing why we're interested in these topics before I define what actually polylogs and elliptic polylogs are. So the theme of the school are, of course, amplitudes. And so what we want to do most of the time is compute amplitudes, scattering amplitudes, where we have external quark gluon states. That's what we usually want to do, be it in the context of N equals super Young Mills, or in the context of more realistic theories like UCD, because we want to compute scattering processes for the LHC. And in that context, well, we usually use perturbation theory. For example, if we want to compute the 2-to-2 scattering amplitudes, then, well, the amplitude A, we expand it into a perturbative series organized according to the number of loops that my final diagrams have. I guess this is something that everybody knows. For example, if you consider 2-to-2 scattering of two quarks, well, the leading approximation at 3 level would be this diagram here and similar diagrams. Then the next term in the series would consist of one loop diagrams where you have one additional gluon exchanged. Next would be two loop diagrams where you have two additional gluons exchanged, and so on and so forth. And it is just a fact of life that the complexity of these diagrams that we compute goes very, very quickly with the number of loops. In general, you can say that computing 3-level amplitudes is easy. Computing 1-loop amplitudes is, well, today I would say it's not easy, but it's also not particularly tough anymore. But everything that goes beyond one loop, you can qualify as hard, and everything that has more than 2 loops is definitely very hard. And so why is it so hard? Well, one of the reasons is that naturally beyond 3-level, you have to compute what is called Feynman integrals. And just to set the scene, let me define what they are. So here you see, for example, the 1-loop integral, a 1-loop 3-point function. And for simplicity, let's assume that all the propagators are massless. And well, you have this 3-point function. And you have to integrate over the momentum flowing in the loop, because that one is not fixed momentum conservation. So you have an integral over the momentum of the particle in the loop, and you have the 3 propagators which correspond to the 3 sides of the diagram. Now, you know that in general these diagrams diverge and to be regularized. I'm not going to talk about that here too much, but I want to focus on what comes out of this integral. So the first thing you can say that's quite easy is that this integral is Lorentz invariant, and therefore, well, naively, it was a function of the 3 external momenta, but by Lorentz invariance, it can clearly only depend on the ratios between the invariant masses. So P1 squared divided by P3 squared, P2 squared divided by P3 squared, or the dot products. But you can easily check that for the 3-point function, all the dot products, you can write them just as linear combinations of the invariant classes. So you're looking for a function of these two ratios. Well, there's an overall scale, which we don't discuss, but the non-trivial function dependence in these two would be in these two variables u and v. So what kind of function could it be? Well, just from physics principles, we know that it cannot be a simple function because unitarity tells you that your amplitude must have these continuities. So amplitude, for example, here 2 to 2 amplitude has discontinuities which come from intermediate particles going on shell. And the discontinuities themselves are proportional to 2 pi r. And so if it was a simple function, like a rational function, then this property could never hold. So it clearly cannot be a simple rational function or something like that. It must be something more complicated. It must be a function that has discontinuities proportional to 2 pi r. And of course, we know such functions. Those are, for example, logarithms. And indeed, when you look at this 3-point function, you see the analytic result in 4 dimensions. It involves indeed logarithms. The arguments of the logarithms, I write them here in terms of these variables z and z bar, which are related to these ratios u and v that I shown here. But it's not just logarithms. There are logarithms, but not only. There are also these other functions like Li2. And there's even in front, there's some rational function. So we have the logarithm, which I show you here. Well, the definition is a bit academic, but the definition I show you here will be useful later on. The logarithm you can think of as doing an integral of 1 over t. So that's my definition of the logarithm. And if you take that definition, then the dilogarithm, this Li2 function, which I guess many of you have heard about before, the dilogarithm you can think of as integrating the logarithm once more. So in the integrand, you have a log, and then you multiply it by another 1 over t, and you integrate once again. So you get a double integral of precisely the kind of integrands that you had before. So we have discovered now at least 2 functions that show up. In general, many more functions show up. In general, I mean beyond one loop. At one loop in 4 dimensions, these 2 functions, log and dilog, are enough. Beyond one loop, they are not enough. So, for example, you may have generalization of this dilogarithm to Li(n). So before we had Li2, Li1 is the logarithm. And so you just extend this definition of Li2 to Li(n) by just recursively integrating the same class of functions over and over again by multiplying with some kernel, which is here dt over t. And in general, all of these functions that we've seen so far, they are examples of something much bigger, which are iterated integrals. So you see a very general and abstract definition down here. So an iterated integral, think of it as follows: you take some functions, and then you iteratively integrate the same function where you removed, in this case, f1, and you multiply it here, and you integrate between 2 boundaries. That's the most general definition of iterated integral. You can imagine it's a very basic definition. And you can easily check that all of the examples that we had are of this type. For example, you can check that in this notation, log x would be the integral from 1 to x of, well, a function of 1 of t dt, where f1 of t is just 1 over t. Or e2 of x would be the integral we had from 0 to x dt over t, integral from 0 to t dt over t of 1 minus prime. You see here this is f1, and this would be f2. So f1 would be would be 1 over t, and f2 would be 1 over 1 minus t. So all of these functions that we've seen here are examples of iterated intervals. And the goal of this lecture, you can think of it as defining and studying some classes of iterated integrals that show up in multi-loop computations. And the three classes that we cover, at least we try to cover as much as time allows, are called multiple polylogarithms, and the elliptic generalizations, and iterated integrals of Euler. So they're all different incarnations of this very general class of functions called iterated integrals. I should also point out that there's a strong overlap with these lectures, with the lectures by Ruth Brito and Eric Panzler here at the school. And you should see these three lectures essentially complementary to each other. Okay, so let's start then with the first and simplest class of iterated integrals that show up in multi-loop computations, which are polylogarithms. So, what are polylogarithms or multiple polylogarithms? You see the definition here, and well, you can see they are, definition is this recursive definition that we've seen before. So you have these functions called g, and you fix, say, some complex numbers, which may themselves be variables of other functions. You fix an upper integration limit. And now you recursively define a class of functions by splitting off, say, a1, and you replace it with 1 over t minus a1. So f1 in the general definition I did before would be 1 over t minus a1. Now, there are some caveats here in this definition, namely if an, the last index, is 0, you can check that the integral will diverge. You need the regularization prescription. As far as I know, Eric will cover this in his lecture, something called tangential base point regularization. I'm not going to give you the details of that here. Here, I'm just going to tell you that the rule that follows from this is that whenever you have a multiple polylogarithm where all the arguments are 0, it is just a power of log. And that is then enough, because now if an is 0 here, while you use the recursion until you get to something where all indices are 0, and you use the rule shown at the bottom of this slide. Now, it's of course not an accident that multiple polylogarithms are also polylogarithms, and we had polylogarithms before, it's usually n functions. So we from now on use the abbreviation MPL for multiple polylogarithms. And they are natural generalizations of the logarithm and the polylogarithm function that we had before. There's log and ln we had before, and you can show that the two relations shown in this slide hold. If you have a polylogarithm of weight 1, that is just a logarithm. And I should have maybe said here that the weight is the number n of integrations. So every polylogarithm of weight 1 is a logarithm. And if you have all the indices equal to 0, but the last one, which is 1, then it is this ln function up to a sign. So the polylogarithms, multiple polylogarithms, contain the logarithms and these ln functions in special cases. Do they contain more? Well, up to weight 3, it turns out that they don't. Starting from weight 4, you get new functions. Now, this is actually a consequence of a much more general conjecture by Goncharov, which was proven think last year by Danil Rudenko, which states that for any weight n, you can always, well, have the number of elements that are non-zero is at most the weight divided by 2. So if the weight is 2, the number of elements that are non-zero is at most 2 divided by 2, 1. So there's always at least one of the two that is 0, and therefore you get 0 something that is classical Lie 2. For weight 3 also, because 3 divided by 2 is 1.5, so 1, most one of them is non-zero. So you get 0, 0 something that is Lie 3, but starting from weight 4, it could be that 4 divided by 2 arguments are non-zero, and therefore you can have 2 non-zero elements, while for these Liens you would need 3. There's a paper by Danil Rudenko on this last year. It's called Conjure of Steps Conjecture. So we have already said that polylogarithms, the examples of iterated integrals. Now there's a more general theory of iterated integrals that maybe Eric will cover in this lecture, but I'm not sure. And there are several properties that iterated integrals have in general, and therefore all multiple polylogarithms have it as well. One of these properties that I want to mention here is the shuffle product, or the fact that iterated integrals in general and multiple polylogarithms in particular form so-called shuffle algebra. What is that? Well, if you multiply two polylogarithms where the upper integration limit is the same, so they have the same upper integration limit, but possibly different indices, and you have both weight 1. What do you get? Well, you get, in this case, you can show you get a sum of two polylogarithms of weight 2. Namely, you get this B, you get A, B, B, A. So A times B is AB plus BA. You can also check that if you multiply A, B, C, what you get is A, B, C plus B, A, C plus B, C, A. And if you multiply AB times CD, I'm not going to color it because otherwise it's going to be too long. What you get is ABCD plus ACBD plus ACDB plus CABD plus CADB plus CDAB. Now this sounds complicated, but it's actually very simple. The combinatorics behind this is actually quite simple. Namely, it is, as the name says, it is the algebra structure behind the idea of shuffling cards. So imagine, for example, you have two decks of cards. You have a deck of cards with a card labeled A, and a deck of cards with a card labeled B. What are all possible ways of shuffling these two decks of cards? Well, there are only two possibilities. Either you put the card A on top of the card B, or the card B on top of the card A. Now imagine you have two decks, one which has one card A, another deck with two cards B, C in that order. B is on top of C. What are all possible ways of shuffling the two decks? Well, either you put A on top, that is what is here, or you put A in the middle, or you put A at the bottom. And the rule to multiply polylogarithms, or more generally iterated integrals, is not more complicated than that. And you can easily check, and I urge you to do this as a homework, that indeed the formula you see here for AB times CD is the 6 combinations you get on the right-hand side, is precisely what you would get from shuffling 2 decks of cards. Good. So now there's a lot one can say about polylogarithms. The mathematics behind them is well understood. There were in the last couple of years several lectures that I gave also where I covered polylogarithms in detail. You see here links to these lectures. One was last year at the ICTS in Bangalore. There's another one that happened exactly 2 years ago in Hamburg. This is school of the Sagix network. And there's also a school that was a bit longer ago at the Tarsi school, and there are proceedings which you can find in the archive. For the other two, you can just use Google, and you find them the recordings of the schools in Bangalore and in Hamburg online. So I mentioned that because those lectures were much more focused on polylogarithms, and so many things, many examples are worked out in detail. I urge you to look at those lectures. And I will here only briefly mention the main ideas of the mathematics behind it, so that I have time to cover other topics which go beyond polylogarithms, in particular elliptic polylogarithms and modular forms. So I will be a bit quick for the details and for many examples behind what is following now on polylogarithms. I urge you to look at these lectures. So, as I said, I will be a bit quick on the polylogarithm part, but there are many lectures in those, and I urge you to look at it. So the first thing that we can say is that the multiplication of polylogarithms preserves the weight. So this, you can think of it as shuffling cards preserves the number of cards. So if you have 2 decks of cards, one with 3 cards and the other one with 5 cards, all possible ways of shuffling these decks will always result in decks that have 3 plus 5 equal 8 cards. We can say that the multiplication of polylogarithms preserves the weight. Weight, we said, is the number of integrations, which in this analogy with decks of cards corresponds to the number of cards in the deck. And let me define the following thing. Let me define AN to be a vector space, and I use as scalars, the rational numbers, spanned by all polylogarithms of weight n. A0, I will just say it's the rational numbers. And I define A to be the direct sum of all of these spaces. So you can think of that as the vector space of all polylogarithms. Saying that the multiplication preserves the weight means mathematically to say that A is a graded algebra. If you look at textbooks, this is often expressed in this statement. So polylogarithms form a graded algebra. But there's more structure. And to understand it, let's first elaborate a bit on this idea of an algebra. So first of all, an algebra, I guess you all know what it is. It's a vector space with a multiplication. And I think of a multiplication now as a map mu, which is linear. It goes from A tensor A. So if you don't know the exact definition of a tensor product, think of it as pairs, and it returns an element in A. So I take a pair of elements in A and I return an element in A. But of course, not in a random way, but I want it to be associative. So I want, for example, that if I take a triple, ABC, and then multiply the first two together, so I multiply AB together, and then I multiply in C, I must get the same as if I first multiply B and C together and then I multiply E. So that's multiplication with multiplication. So I can express associativity through this diagram. Now, it's useful, or it will be important, also to talk about what's called co-algebra. Now, whenever you see in algebra, you see words starting by co, it means that you should, everything goes in the opposite direction. So in algebra, we say we take a pair and we turn it into one object. The co-algebra, we take one object and we turn it into a pair or a sum of pairs. In this operation, we call it the co-product. And the experts know that there's also something like a co-action. I will comment on that in a second. And just like associativity was part of the definition of my algebra, my co-algebra will have co-associativity. And I just have to take the diagram that I drew for associativity and reverse all the arrows. So co-associativity, in words, it means it doesn't matter how you iterate this procedure of splitting things into two, because once I have a rule that allows me to split things into two, I can turn it into a rule to split things into three, and so on. And it just means it doesn't matter how I iterate it. So at first, if I split things into two with my core product, and then I split it into three by acting with the core product in the first two entries, from here, here. Or if I act with delta in this slot to split it into these two, the answer will be the same. So just like associativity tells me that for multiplication, it doesn't matter in which order I multiply things together, co-associativity says it doesn't matter in which way you break it apart. The result that you get is unique. So why am I telling you this? Because, well, we have seen that polylogs form an algebra, shuffle algebra if you like. But they also form, well, a Hopf algebra. A Hopf algebra, think of it as, it's a bit naive, it's not quite that, but it's good enough. They form both an algebra and a co-algebra. So there's both a way to multiply them and a co-product that allows you to break them apart. And well, I refer you to some of these other lectures that I mentioned to get details. But just to give you some examples, for example, the co-product of the log, which is the simplest functions, well, the co-product breaks things into simpler pieces. That should be the naive idea. Now the logarithm should be the simplest thing that I have in my polylogarithm. So I don't expect that I can break it into anything simpler. And indeed, the co-product of the log is a sum of two pairs where the first slot contains nothing, meaning one, and the second slot contains the whole function. Or the first slot contains the whole function, and the second slot contains nothing. Good. Another example would be, well, the next most complicated. What about the product of two logs? And here should tell you that I require that my co-product respects multiplication. And well, the elements delta V and delta V are tensors, so I also have to tell you how you should multiply things like this. And well, those who know about tensor algebras know that the rule is to just do it component. And I leave it to you as a homework to show that if you use these two rules, if you use what you know about the logarithm from here, together with these two rules here, you can show that this relation holds. Good. So that I leave it to you as the homework. So let's look at the next interesting example, which would then be another way to function, which is sweep2. Now, one thing which you can see is that one way to break things into two is always not to break it at all. So there was always this term, these, let's call them trivial terms. They also appear for the dilogarithm. But for the dilogarithm, there's also now a non-trivial piece that appears where I break the dilogarithm into a pair of two logarithms. Why these two? Well, you can, that for that you need to go to the general theory that can be explained. If you want the details, I suggest that you look at one of the other lectures. There's some details about this are given. Otherwise, you can just take it as a fact. There's also a general formula for the co-product of Lie, which is the generalization of what we have for E2. So there's one important thing. And again, I will be quick. I urge you to look at the other lectures, but also Ruth in her lecture, she will have a whole lecture devoted to the co-product and co-action. So she will pick up many of the things that I'm saying here, but I think it's good to put it into context. So that's why I'm only showing you formulas. But the one thing I want to point out is the following. So there's this general formula for the co-product of Lie. That's what must hold. So there were these always these trivial terms, and then these other terms where to break things apart. Now this was hold for every x, so I should be able to specialize x to something. And in particular, let me put x to 1. And I think many of you know that if you evaluate Ln at 1, you get Zn. If not, I'm telling you that if you evaluate Ln of x at x equals 1, you get the Riemann zeta function evaluated at n. Now I can do that for all the terms in here. So I can do it for the first term, for the second term. I can also do it for the last term, but now you see I have log of 1, which is 0. And something tensor 0 is 0. So all of these terms in this sum drop out, and only these two trivial terms remain. So I conclude that the co-product of Zn is 1 tensor Zn plus Zn tensor 1. That's good. To become simple. That's what I expect. If I specialize, it should not get more complicated, it should get simple. But now recall that Zeta2 is actually pi squared of 6. Zeta4 is pi 4 over 90. So you can relate them in the following way. But now recall this rule that we had 2 slides ago about delta of A times B. Well, delta is linear, so I can just pull out the 2/5. And delta respects multiplication, so I can just pull out the square. But delta of Zeta2, well, so I can evaluate it, delta of Zeta2. And if you do this exercise for log x times log y, and you do exactly the same thing here, you get to the following result. But that's a problem, because that is a contradiction to putting n equals 4 in here, because I have this other term. Okay. So something is not quite right. Somehow I need to kill this term, Zeta2 tensor Zeta2. Now, the way to do it, well, if you look at Goncharov's original paper, it explicitly states that Zeta2 should be considered 0, or pi 0. Why pi? Well, remember, 2 pi I is the discontinuity, so it has to do with discontinuity. So saying modulo pi means modulo discontinuities. In a more modern version, which goes to, let's say, some extent back to Francis Brown, you would only say you work modulo pi, so modulo discontinuities in the second entry, not in the first. So you would only say this guy is 0, but not this guy. So in other words, you would say, if you only say you would then say that, well, remember that we said delta of zeta n was 1 tensor zeta n plus zeta n tensor 1. So if n is even, zeta n is proportional to some power of pi squared. But I should work modulo pi in the second entry, so I should drop this term when n is even. And so I'm left with delta of zeta 2 is zeta 2 tensor 1, delta of zeta 4 tensor 1, and so on, or more generally, delta of pi or I pi is I pi tensor 1. This will come back in Roos's lecture substantially, and is actually very important if you do explicit computations. Now, technically, I should say that all I said, I was really oversimplifying. The polylogarithms do not form a Hopf algebra, they form what is called a co-module. And it's only the polylogarithms modulo discontinuities that form a Hopf algebra. For the details, you can, for example, look at papers with Francis Brown. For all practical applications, 2 polylogarithms consist 4 polylogarithms. It is enough to use as a practical tool, as a calculation tool, the idea that all the formulas work as if it was a Hopf algebra, except that in the second entry, or in all entries for the first, rather, you have to work modulo pi, modulo conjugates. Good. As I said, this will come back in Roos's lecture substantially. Now, the last topic, which I just want to touch upon for polylogarithms, is something many of you, I guess, have heard, is called symbols. Now, so first, remember that the coaction allows you to take a polylogarithm and to decompose it into polylogarithms with lower weight. For example, Li2, I could turn it into a tensor product of 2 logs. That's what we did here. For Li3, I can now decompose it into, well, they're always my trivial terms, which would be those 2. But now I would have terms where I have a weight 2 function in the first slot, a weight 1 function in the second, or the other way. Now I can iterate that. I can, for example, take here this weight 2 function in the first slot and act again with the coproduct and decompose this 2 into a 1, 1. Or I could do that in the second slot. But my coproduct is co-associative, so it doesn't matter in which way I do it, I always get the same answer. In particular, there is a notion of maximal decomposition, if you want, where you've taken a weight n polylogarithm and decomposed it into n weight 1 functions, n logarithms. And that object is called the symbol. And you should think of it as some kind of invariant attached to a polylogarithm. For example, the symbol of the logarithm is just the logarithm, because the logarithm is the building block of the whole thing. It's a weight 1 function. The symbol of the dilogarithm is a pair of logarithms, and you can compare it to what you have in the coax. You see it's exactly that quantity. In general, the symbol of Ln is the following. And I leave it to you as a homework to prove this identity. Now, for those of you who are familiar with symbols, or if you look at the literature, then it is often, I think I lost connection. Can you still see the screen? I think I lost.
I see something on your iPhone or iPad.
Yeah, let me maybe stop the synchronization, stop screen sharing and share it in here somewhere. Perfect. Good. So in the literature, you often have symbols denoted in such a way that you drop the log symbol, because you see it's a bit redundant to write log, cancel log every time. So in the literature, you often see the note in this way. Now, the properties of the symbol are directly inherited from the correction. So, for example, we all know that log A times log B, where log A times B is log A plus log B. And if you remember that this entries in the symbol here should be logs, it's not surprising that if you have A times B somewhere in the symbol, you can just take it apart, edit it. Since log of 1 is 0, and log of 1 is minus 1 is I pi, and I pi, I put it to 0. Whenever you have plus or minus 1 in a symbol, you put it to 0. The symbol of the zeta value is 0. Why? Well, because I cannot decompose into logs. We said that zeta n has this very simple decomposition. And another rule, which again I leave you as a homework, is to show that if you take two functions f and g and you multiply them, and then you take the symbol, you get the shuffle of the symbols of f and g. So for example, log x times log y, its symbol is x times y, x tensor y plus y tensor x. So this is exactly the same rule as with shuffling. Good. So I think this is a good moment to take the break. And then this was also all what I wanted to say is a very basic introduction to polylogs. And I suggest that for details and many examples and exercises, we look at the lectures that I showed at the beginning of the section polylogs here in this lecture. So there were the lectures in Bangalore, the lecture at the Sage School in DC, and also there's the archived version of the Tazi lectures. And then in the second part of the lecture, which will start after the break, we will look at generalizations of polylogarithms and what their properties are. Okay, so this is a good place to take a break.